Okay, today we'll have a presentation by group, okay, on the project. So at first you have to identify the problem and take a case study, and you have to use the advanced analytical model. So try to get the data sets and provide detailed solution using deep learning techniques in artificial neural network. Okay, and then you have to provide step by step on how data be analyzed with deep learning, right? You can use this guide as a cross-industry standard process for data mining, where you can use for your project. Alright? And today we will have a project presentation with the project leader and the group members. Okay? Okay, thank you.
Salam sejahtera, Doctor. My name is Liew Kai Wen from S1G2 Group B. Today, our group will present the title of Brain Tumor Detection Neural Network Model. So, my teammate Liew Kai Wen, Sun Wei Hong, Rong Jie and Lui Qi Zhe. Next is our problem statement of the project. The goal of our project is to detect the brain tumor from MRI scans accurately by using the CNN, which is convolutional neural networks. So the challenges we face is data imbalance. So to overcome it, we can make sure the data of every class is balanced by using the resampling dataset. So next is overfitting. Overfitting will lead to bias or poorly generalized models. To overcome it, we can split the dataset into training and testing set. For example, we can split the data into 80% for training and validation data and 20% for the testing data to evaluate the model more better. So the last challenges is underfitting. Underfitting will cause poor performance on both the training and testing data sets. So to overcome it, we can train the model for more approaches and reducing the regularization strength, and the model complexity can be increases by adding more hidden layer. So next is our introduction. So in our introduction part, as we all know that brain tumors are life-threatening, making early and accurate diagnosis is important for the patients. So traditional manual MRI analysis is subjective and prone to many errors. This report explores using CNN, convolutional neural networks, and AI deep learning technique to automate brain tumor detection from MRI images. And the goal is to develop an accurate CNN model that can distinguish between tumor and non-tumor images, offering a faster and more reliable diagnostic aid for healthcare professionals. The tools that we use in our project is Python, TensorFlow, Keras for the model architecture design and training. Next is OpenCV for image processing transformation, and the last is Sklearn for the data partitioning part. Okay.
First of all, let me introduce our deep learning model design, which is CNN, Convolutional Neural Network. Our CNN model defined with L2 regularization that include several layers, input layers, hidden layers, and output layers. For our input layer is the product of the image height, width, and number of channels. For the hidden layer, we include 3 convolutional layers to finding the important patterns like edge and texture in the image. One filter layer prepare the processed image feature so they can fit into the next layer. Then one dense layer in the hidden layers learn how to combine them to make the tumor or not tumor final decision. Our regularization using the kernel regularizer value is 0.01. Then the dropout value we set to 0.6 to get a better performance. Lastly, we have one output layer which is a dense layer with CMOS activation. So what is CMOS activation? It's a special function that helps the neuron decide how much of the data should be passed forward. So let's move on to the training method. Our training method used in this project is data augmentation. We set the database to 128 to get a better performance. Then export is maximum approach is 30 lah. Then for the validation, we separate the dataset with early stopping and reduce LR on plateau. What is early stopping? For example, we set the patient to 10. After 10 exports with no improvement for the accuracy, then the training process will be stopped early. Then how the augmentation trains the model? By using random, rotation, zoom, shift, and horizontal flip. So this can increase the diversity of data without increase the sample. So this can make the training process more efficiency. That's all for our model setup.
Okay, now let's look at the key takeaways from our project. First, our CNN model demonstrated strong capability in identifying brain tumors, especially evident from the high recall rate for yes tumor cases. This means that the model is effective at minimizing the false negatives, which is extremely important in the medical diagnosis. Second, while the model performs well overall, there is still room for improvement in distinguishing non-tumor cases. The precision for no tumor is slightly lower, indicating that the model occasionally flags healthy scans as tumors. Third, visual tools like the confusion matrix and training history plots provided invaluable insights. For example, they help us identify mal-overfitting, where the model slightly favors training data over unseen validation data. Fortunately, it wasn't severe, and techniques like dropout, data augmentation, and early stopping help mitigate it. Overall, the takeaways confirm that our CNN approach is promising for brain tumor detection.
Selamat sejahtera Doktor, I'm Liew Kai Wen. So this is our plot training history for our accuracy over epoch. The trend this graph shows that the model's training and validation accuracy improve over epoch, indicating effective learning. And the graph shows convergence. Both curves stabilize at around 78 to 80%. This suggests that the model reaches a reasonable performance plateau. There's a small gap between the training and validation that indicates minor overfitting, but it's not that severe. This is the plot training history for our loss over epoch. There's some training loss, but it decreases steadily from 1.3 to 0.5. This shows effective learning. The validation loss improves initially but plateaus around 0.7 after epoch 15. There are some key insights to this graph. There's the growing gap between the curves that indicates mild overfitting. The solution to solve that problem is to add a dropout and use early stopping or augment data to improve generalization.
Salam sejahtera, Doctor. My name is Sohen Ho. Now let's dive into the details of our model performance with the confusion matrix. So this matrix is a powerful tool that visually summarizes how well our classification model performance by showing the counts of true positive, true negative, false positive, and false negative prediction. So looking at the matrix, we can see in the top left quadrant, the 250 instances where our model correctly predict the non-tumor when the actual label was non-tumor. These are our true negative. So moving to the top right, we have 85 instances that were actually non-tumor but our model mistakenly predict yes tumor. So these are our false positive. So in a medical context, this means a healthy patient might be incorrectly identified as having a tumor. In bottom left, we see 40 instances where the actual label was yes tumor, but our model predict no tumor. These are our false negative. For brain tumor detection, minimizing the false negative is critically important as it means a tumor could be missed. And finally, in the bottom right, we have 260 instances where our model correctly predict yes tumor when the actual level was yes tumor. So these are our true positive. From this matrix, we can further confirm the insight from our classification report, particularly that our model performs better at detecting tumors, as indicated by a higher number of true positive and a relative lower number of false negative for yes tumor compared to the false positive for no tumor.
So now let's go to our conclusion. So to conclude, let's summarize the key achievement and the technical strength of our brain tumor detection project. Our primary achievement is the development of a high-performance model. So it achieved an impressively 80% validation accuracy with 0.98 confidence in the tumor detection. What especially crucial for medical application is the demonstration of a low false negative rate, which is vital for accurate and reliable diagnosis. From a technical standpoint, the choice of a convolutional neural network or CNN proved to be a significant strength. CNN offer several advantages. First, they enable automate the feature extraction from MRI scan, reducing the need of a laborious manual processing. This also lead to minimal manual pre-processing and contribute to the model robust generalization capabilities, meaning it can perform well on new unseen MRI image. In essence, we develop an accurate CNN model capable of distinguishing between the tumor and non-tumor image, offering a faster and more reliable diagnosis for healthcare professionals. That's all for us. Thank you.